Thwaites has earned the moniker Doomsday Glacier.
It's the largest, most menacing source of rising sea levels all over the world.
It's already dumping 50 billion tons of ice into the ocean each year.
They estimate the ice shelf on Antarctica's massive Thwaites Glacier could collapse within the next 5 years, causing a dramatic sea level rise.
They're calling it the Doomsday Glacier.
Hi, I'm Mikhail, your climate host for this virtual field lab series focused on sea level rise and Thwaites Glacier in Antarctica. You may remember from the first 2 episodes that I'm an architecture student, not a climate scientist. But I'm interested in Thwaites because, like everyone else on the planet, if Thwaites really does deserve the Doomsday Glacier nickname, then we will all see big changes in sea level rise in our lifetime. For me, that means job security as I help redesign coastal regions to become more climate resilient. For millions of other people, that means things like higher insurance rates, having to spend money to raise an existing home above the rising seas, or even bigger changes like migrating away from threatened coastal areas to areas less likely to experience catastrophic flooding. In episodes 1 and 2, we analyze the stability of Thwaites using 2 vital signs: the speed of the glacier, and the size of the remaining eastern ice shelf. Unfortunately, both of those vital signs indicate that Thwaites is not a healthy patient. Having data for this 3rd vital sign will help us determine if the nickname Doomsday Glacier is just hype or actually well-deserved.
Thanks, Mikhail. Like Mikhail said, the first 2 vital signs that we looked at for Thwaites Glacier are pretty concerning. In the first episode, we learned about how the Thwaites Eastern Ice Shelf has a really complex flow history, but we can see that it's been accelerating a lot in the past several years. We also know that the ice sitting on land, the grounded ice, has been speeding up, including in the main trunk, which used to flow into the Thwaites Western Ice Tongue before it completely fell apart. In the second episode, we could see that the Eastern Ice Shelf also seems to be falling apart. It's lost a lot of its area in a very short amount of time. We've also talked about some key areas that we're watching really closely to understand the changes we're seeing on Thwaites Glacier and the Thwaites Eastern Ice Shelf. The first area is the grounding line, which is where it goes from sitting on land to floating as part of the ice shelf. The second is at the seaward edge of that ice shelf, where it runs aground onto sort of islands, but they're below the surface of the ocean. Where it runs aground, it's sort of pinned in place, so we call this the pinning point. And the vital sign that we're going to look at today is the stability of the ice around this pinning point. The satellite images that we'll use today are the same ones that we used in episode 2, and you can see a lot of the important features of the ice shelf in these images, including sea ice off the coast, which formed out of ocean water, icebergs that have broken off of the ice shelf, smooth, intact ice on the ice shelf, and crevasses in areas where the ice shelf has started to break apart. For this investigation, we're going to look at the crevasses forming near the pinning point. If the number of crevasses stays the same, that would tell us that the ice shelf is stable in this area. But if the number of crevasses increases, that would tell us that the ice shelf here is becoming less stable. Let's write this question down in our notebooks. What do the number of crevasses near the offshore pinning point tell us about the stability of Thwaites? Now I'll turn it back over to Haley, Evelina, and Samsara, who will take us through this investigation.
Hi, my name is Haley.
My name is Evelina.
And my name's Samsara.
And we're all seniors at Grant High School in Sacramento, back to help you with the 3rd analysis of the vital signs from the Thwaites Glacier.
In this episode, Karen and Richard asked if we could help analyze the stability of the ice shelf at the offshore pinning point.
The offshore pinning points are shown on the map as a red circle. The pinning points are actually underwater islands where the glacier is stuck.
One sign of instability around the offshore pinning point are crevasses. Crevasses are large cracks in the ice that can propagate or spread all the way through the ice shelf. Crevasses are a normal part of the life of an ice shelf and usually appear near the ice front. Crevasses usually result in large icebergs breaking off of the ice shelf and floating out to the sea. When a glacier is stable, the number of crevasses are fairly constant. But when a glacier is unstable, the number of crevasses increases. For this analysis, we'll be using a collection of satellite images taken over the past 20 years to count the number of crevasses near the offshore pinning point.
To be consistent, we'll first need to standardize where we count. I'll overlay a search area box on each image. We'll also need to standardize what we'll count as a crevasse. When a crevasse spreads to the surface, it opens up a crack in the snow, which shows up as a dark line on the satellite image. You can see a crevasse here on the satellite image. You can also see a real crevasse out this plane window that's flying over Thwaites.
For this investigation, we'll count visible crevasses that meet 3 criteria. First, they must run approximately parallel to the flow of the ice sheet.
Second, they must be at least 1 kilometer long.
And third, they must have reached the surface and appear dark on the satellite image.
Let's add a data table to your notebook to record our measurements. On the left, we could put the year, and on the right, we could put the number of crevasses. We'll measure the same years as the first 2 episodes. Pause the video if you need more time.
I'll make the first 2 measurements and then bring up the rest of the satellite images for you to analyze on your own. Here's an image of the ice shelf taken in 2001. In this image, we can see 2 crevasses that meet all 3 of our criteria. In this top corner, I can see 2 crevasses that have broken through the surface and appear dark. Both are at least 1 kilometer long and both run parallel to the flow of the glacier. Let's put this in our data table.
Here's the next image taken in 2005. In this image, I can see that there are crevasses in the top and bottom of the search area. I will count that there are 4 crevasses at the top and 3 at the bottom. That would be a total of 7 crevasses. Remember, this is not exact science, so our measurements might be slightly different. Next, we'll bring up 5 more satellite images taken between 2009 and 2022. I'll leave each image up for about 10 seconds. If you need more time, just pause the video. When you're done counting all the crevasses, we'll meet back here, we'll compare numbers, and make a graph.
Welcome back, and nice job on making all those measurements. Let's compare data. Here are the measurements that I made. Hopefully our data looks similar. Just looking at the data, it seems like there's a trend, but I still think it helps tell the story better if we put the numbers onto a graph. If you want, you can add these data into the graph you made in episode 2, or you can make a completely new graph. I'm going to use the graph I made in episode 2. Our independent variable, time, will go on the x-axis, and our dependent variable, the number of crevasses, will go on the y-axis. Since I'm using the same graph, I'll put the number of crevasses on the right axis. I'll also use a different color. We can use a scale for the number of crevasses that goes from 0 to 25.
Pause the video while you build your own graph. Make sure to include a trend line that you think best shows the story of the data. When you are done, hit play and we can see how our graphs compare. Welcome back and nice work. Let's compare our graphs. Drawing a trend line through the data was definitely a bit of a challenge. Here's how I saw the trend in the data. It looked like to me that the number of crevasses were fairly constant in the beginning, however started to increase as we got closer to 2022.
Let's add 2 more notes to your graph before we wrap up. First, let's add a note to your graph in 2009, the year that the western ice shelf collapsed. Next, let's add labels that show the relative stability of the ice shelf based on the number of crevasses. In the early years, the ice shelf had fewer crevasses, suggesting that it was more stable. The high number of crevasses in the recent years indicates that the ice shelf is becoming more unstable.
Before we turn this back over to Karen and Richard, we'd like you to take some time to analyze your data. In your notebook, write down 2 things you notice and 1 thing you wonder. You can pause the video while you write. When you're finished, hit play again and Karen and Richard will come back to wrap up the episode and this series. Thanks for doing science with us.
Thanks, Haley, Evelina, and Samsara. When I look at the data we've collected here, I get pretty concerned. We're seeing big increases in the number of fractures near that pinning point on the Thwaites Eastern Ice Shelf. When you combine that with our observations that the speed of the ice shelf is increasing and the size is decreasing as icebergs calve, we can tell that this ice shelf should have our full attention. All of the vital signs that we've looked at have focused on the surface of the Eastern Ice Shelf, but there are really important things happening underneath. The changes that we've been observing on Thwaites Glacier have been caused by a change in ocean circulation that has brought more relatively warm water into contact with the grounding line and the base of the ice shelves. This warm water is responsible for these really complex changes that we've been observing. The warm water has melted the ice shelf to the point that it's thin enough that it's falling apart, and the Thwaites Eastern Ice Shelf might collapse in the same way that the Western Ice Tongue did more than a decade ago. Even more concerning is what that relatively warm water will do to the grounding line, which is that area where the ice goes from sitting on land to floating. As that warm water has come in, it's caused melt, which has made the grounding line retreat or move upstream. It changes a lot over time and over space, but in some places that retreat has been as much as almost a mile per year. These really fast changes might get even more complex if the Eastern Ice Shelf collapses and exposes the grounding line to new forcings. This is an area of active research that we need to pay really close attention to, because the faster that grounding line retreats, the more ice is added to the ocean from the reloading zone, and the faster sea levels rise. The future stability of the Thwaites grounding line is one of the big contributors to the large uncertainties in future projections of sea level rise. Even in the best case scenarios, we need to be planning for maybe 1 to 2 feet of global sea level rise by the end of this century. If we continue to warm the planet very rapidly, and if Thwaites responds very sensitively to those changes, we could see more like 7 feet of sea level rise by 2100. And there are some processes that we don't understand very well yet that could push that sea level rise even higher in our worst case scenarios. So does Thwaites Glacier really deserve the nickname Doomsday Glacier? It's certainly changing very rapidly, and it has big controls on what's going to happen with future sea level. But whether it really is a Doomsday Glacier might depend on what we as humans do. Let's turn it back over to my dad, who will finish up. He's got some ideas about the future that might give us a little bit of hope.
Thanks, Karen. When we refer to Thwaites as the Doomsday Glacier, it can seem like there's little hope for the future. But all of us working on this project are fortunate to know better. We can take actions to help ensure Thwaites against collapse while helping build a better world. The climate is changing rapidly now because we humans are burning a lot of things to release their energy, increasing levels of carbon dioxide in the atmosphere. For perspective, you can see the trash we throw away, and you know how much of it there is. Every year, people in the United States throw away about 1/2 ton of trash each for the garbage collectors. But we're each responsible for about 15 tons of CO2 that we can't see from burning the trainloads of coal and tankers full of oil and pipelines full of gas. The warming, the ocean acidification, and the other changes from this carbon dioxide are already causing bad things. They will get worse as we burn more. So why do we have hope? Many reasons. First, we really can solve big problems. Consider a computer or a smartphone. What is it? It's just a little sand for the glass and the silicon of the computer chip and some organic materials such as oil for the plastic and the right rocks for the rare earth elements and the palladium. And science and engineering and design and marketing, you can have Einstein in your pocket. The GPS uses special and general relativity. And if we didn't understand relativity, the nice person in the phone would begin to get lost in 2 minutes. But it doesn't. If we can do this, we can do energy and climate too. Our history shows that we can innovate on energy. In the 1800s, rich people lit their evenings by burning whale oil. But as whales became scarce, the price of whale oil went way up, and we switched to fossil fuels. When we switched from killing and burning whales, they could recover. A similar story happened with trees. Our ancestors cut down almost all the trees in the eastern U.S. and many other places, driving away or killing most of the wildlife and making fuel scarce and expensive. Where I live, many of the trees were used to make charcoal to smelt iron in early furnaces. Eventually, as the trees were used up, coking coal was used instead, and we let the trees grow back. When we changed our energy choices, the forests and the whales recovered. Now, as we burn through the fossil fuels and suffer the rising seas, increasing floods and droughts and other dangers, we are also finding better, cheaper, cleaner ways to power people. The good news is, just like in the past, we really do have the ability to choose a better energy future. For the first time in human history, we can use renewable energy sources that won't run out and that are available to everyone rather than relying on scarce fossil fuels. We really do know that if we use our knowledge about energy, we can stabilize the climate while building a larger economy, supplying renewable energy that the International Energy Agency called the cheapest electricity in history. Doing this can give us more jobs, improved health, greater national security in a cleaner and more ethical world. It's a huge task, but with even greater benefits awaiting. This future will be built by you, by scientists and engineers, but also by artists and writers, business people and lawyers and doctors and others who will find the win-wins that help people and the environment. So thanks for investigating Thwaites, the glacier that doesn't need to bring doomsday, if we choose to build a better future. The choice is yours, and it may be easy. Just ask a whale.